In this video, we will be introducing circle vocabulary for our next unit, which is all about circles and segments and angles and arcs you can make within a circle, segments and lines and angles that intersect circles, and so on and so forth. Before we define some terms, I'd like to remind us of some algebra that we're going to use, and we're going to use these in particular to solve some problems that are going to naturally arise from the definitions and properties of some of these parts of circles. These are right triangles, so the side lengths are related by Pythagorean Theorem, which is things we've solved quite a bit. I think a squared plus b squared equals the hypotenuse squared, so r squared plus 12 squared equals 13 squared. R squared plus 144 equals 169. R squared equals 25. R therefore is plus or minus 5, but in this context we can only have positive lengths, so R is positive 5. You could alternatively solve this problem by realizing that something 12 and 13 are a Pythagorean theorem, or a Pythagorean triple, specifically 5, 12, and 13. And what do you know? R is 5. A Pythagorean theorem question that's a little bit more algebra intensive is something like this, and this is kind of more so what we're going to see when we set up some of these geometry problems. I think still this is a right triangle, so still a squared plus b squared should equal c squared, or r, in this case, r squared plus 8 squared should equal this entire length squared, which is r plus 4 squared. Note that r plus 4 squared is r plus 4 times r plus 4. And if I use a box or FOIL or whatever your method for multiplying polynomials is, you'll get r times r is r squared. R times 4 is 4r. 4 times r is 4r. 4r plus 4r. And 4 times 4 is 16. And this is equal to r squared plus 8 squared, which is 64. Two things jump out at me. First off, 4r plus 4r can be combined together to be 8r. And both sides have an r squared, so I could subtract that from both sides. And what's nice is this, even though on the outside we thought maybe this is going to end up being a factoring problem and maybe factoring is not my strong suit, it turns out that since I'm subtracting off these r squareds, what looks like a factoring problem is actually not. It's actually just solving this two-step equation. I get r by itself, how about subtracting 16? 48 equals 8r, and divide by 8, and get r is equal to 6. For the rest of this video, we're going to define some terms that are vocabulary terms that relate to circles, and then we're going to apply a couple theorems related to these terms. A circle we'll define as the set of all points that are the same distance or equidistant a center point. And note that this means that we're looking at just the points that are on the outside of the circle. So all the points on the inside, in between the center and the edge of the circle, are not a part of the circle. If you want to talk about all the points up to the edge of the circle, we can think of that as what's called a disk. But if we're talking about a circle, we're talking about just the points that are on the edge. I'm sure you know a few of these terms of radius is just the distance from the center to the edge. To the edge. Diameter is what you get when you put two radii together, or better yet, this is a segment with endpoints on the circle and that passes through the center. Maybe some terms you're less familiar with. A chord is similar to a diameter, but it does not go through the center. This is just a segment whose endpoints are on a circle, but does not pass through the center. A picture of a chord might look something like this. And I'll try to draw a circle up here. We have a circle, and there's a center. Then a chord would be a segment who does not go through the center. Whereas a diameter would be like a chord, but it does pass through the center. A secant is very similar to a chord. However, it's a full line. This is a line that passes through a circle and intersects it twice. Often we think of chords as parts of secants. So a secant might look something like a chord, but instead of just a segment, it's a full line that goes on forever. A secant might go through the center. It might contain a diameter. It also might just contain a chord, but it hits a circle twice. A line that is similar to a secant, but instead of hitting a circle twice, hits it once, is called a tangent. That sects a circle exactly once. What does that have to look like? Well, if I drew a circle and I want a line that hits a circle exactly once, there's lots of ways I could do that, but I think it has to look something like this. I think I need a line, and I need to come really close and just graze the circle and move on. So it needs to just barely touch and then continue on. If you do this and just hit it once, let's call it tangent. If it just intersects it twice, we call that a secant. Some important properties of these. There's a really nice test to see if a line is in fact a tangent and not a secant. If the test of a line intersects a circle exactly once, and that is if a line is tangent to a circle if and only if it intersects the endpoint of a radius, and it does so at a right, and it is perpendicular to that radius. So in order for this to just graze the circle, we have to be able to draw a segment that goes from the center to where that point of intersection is, and we should be able to measure exactly a right angle, or exactly 90 degrees between the line and the radius. Vice versa, if you construct a tangent, then it is forced to be a right angle to the circle. Or if you construct a right angle, then you make a tangent. It works both ways. One final theorem, one final property we should know is that if you have two tangents and they intersect the same circle, what you can show without too much effort is that these two segments you make are in fact the same length. You could do that by, say, connecting the center of the circle to this point where they intersect, and then draw radii from the center to where these points intersect the circle, called the points of tangency. From the previous theorem, since these are tangent, the radius intersects these tangents at right angles. And since the radii are the same length, I think we constructed two triangles that are congruent by hypotenuse leg. Because we have right triangles, the radii are the same length, so they have a leg that's shared, and they have a reflexive sharing of the hypotenuse. Which means that these triangles are congruent, and because corresponding parts of congruent triangles are congruent, we know that these corresponding parts, or namely the segments that go from this point of intersection to the circle, are the same length. Okay. We're going to apply this some vocabulary here, and then decide, then verify if a line is tangent to a circle in the rest of the remainder of this video. Let's see, segment. What is segment PR? Segment PR starts at P, ends at R, and passes through the center. A segment that starts and ends on the edge of a circle and passes through the center is called a diameter. Line MN intersects a circle exactly once. This is a tangent. Segment QO starts at Q, ends at the center. That's a radius. Line PQ is a line that passes through the circle and hits it twice, once at P, once at Q. That's called a secant. Note that if we had done segment PQ that starts at P and ends at Q, this would have been a chord. So it's important to be paying attention to what the symbols are to make sure we know whether we're looking at a line or a line segment. That'll determine whether we're looking at secants or chords or similar. A common tangent is, as you might guess, a tangent that is in common with two or more circles. So you should be able to visually identify where common tangents are possible and where they're at. In this picture, there are no possible common tangents, and you can kind of see that if you were to draw a tangent of the big circle, it will never hit the inner circle, or if you draw a tangent of the inner circle, it's going to hit the outer circle twice. So there's none possible. In this case, I think there's exactly one possible. I think if I'm going to try my best with my computer here to draw one, it might look something like this. In this case, I see not one, not two, but I see four common tangents. I see one on top and one on the bottom. I'm going to draw them the best I can. One maybe looks like this, and another that looks maybe something like this. But I also see two that are kind of diagonal going through it, and I'll do my best, but I'm not very good with the computer pen. One that, well, it should be a little bit further up, but maybe you can see what it's supposed to be. And then another one that I think looks something like this, goes through the center. And again, if I had a straight edge and this would be a little bit better, but I see four. I would challenge you to try to, looking at these, to try to dream up situations where you can draw two circles, but there be exactly two common tangents and exactly three common tangents. See if you can decide what that picture might look like on your own. Lastly, for this video, given a diagram, you should be able to decide if a segment is or is not tangent to a circle. In this picture, segment PT is a radius, and we want to decide is segment or line ST tangent to the circle. We saw from before that if a line is tangent to a circle, then at the point of tangency, it is perpendicular to the radius. So what this problem really boils down to is deciding is this angle STP, is this a right angle? And you can decide that by testing if this is a right triangle. And a test for a right triangle is Pythagorean Theorem. So we need to decide, is a squared plus b squared equal to c squared? Or is 24 squared plus 44 squared equal to the proposed hypotenuse squared, which would be 51? I know, is this true? According to my calculator, 24 times 24 is 576. 44 squared is 1936. And 51 squared is 2601. Without actually adding these together, I can tell right off the bat that they are not equal. The last digits in both of these numbers are 6. 6 plus 6 is 12. That means this number has to end in a 2, but unfortunately it ends in a 1. And by adding them with my calculator, I get 2512, and this is clearly 2601. These are not equal, so this is not a right triangle. Which means that ST is not a tangent.